So in the last video, we saw that on these basic open sets df, every regular function phi has the form g divided by some power of f, where g is some polynomial function. And in this kind of short video, I want to point out that such quotients already appear naturally in commutative algebra in the context of localization. So as a reminder, for localization, if you have R a ring and S a multiplicative subset of R, which means that the product of any two elements in S is again an element of S, then we can define a new ring, sometimes denoted S inverse R, sometimes denoted R adjoint S inverse. And this ring contains elements R divided by S, where R is in R, S is in S. And such fractions modulo some equivalence relation. This will be the localization of R at S. And the equivalence between these fractions here is that there exists T in the multiplicative set such that, I mean, normally you would expect the equivalence should be you clear the denominators and then you would have R1 times S2 minus R2 times S1 should be 0. But and this is okay when R is a domain. But if R is not a domain, then there's this extra twist that maybe this isn't 0, but then if you multiply by something in the set S, then it becomes 0. So this is the equivalence relation. You can check. It has the usual properties of an equivalence relation, and the usual addition and multiplication of fractions gives this a ring structure. And a particular multiplicative set, basically one of the easiest ones you can write down, is that if you have an element of R, then you can look at the set S, which is just the powers of that element. This is a multiplicative set, of course, because the product of two powers is again a power. And you denote the localization at this particular set as R lower F. And well, here we see this is an instance where the denominator is allowed to be some power of this given F, exactly what we see here. And so maybe it's not a surprise that when X is affine and F is an A of X, then the regular functions on df can also be seen as the localization of the ring of all functions, all polynomial functions on all of X at this particular element F. This is an equivalence SK algebras. So before we kind of just saw set theoretically what are all these elements here, and now we have really identified it as a K algebra in terms that we already know. And the idea is you can just write down what this K algebra morphism is. From here to there, this is the natural direction. Is you just take this equivalence class of G divided by F to the M in here. This is the general element there. And you send it to, well, this looks a bit stupid. You send it to G divided by F to the M. But now you interpret this as a function from this set df to K, which sends X to the corresponding evaluation. And so we need to check a couple of things. First of all, that this is a well-defined map because somehow there's an equivalence relation here, as we saw. So assume that you have two equivalent elements in the localization. By definition, this means if you clear denominators, then you're still allowed to multiply by an element of the multiplicative set. So in other words, you're allowed to multiply by a power of F, and then this should become 0. And you want to use this condition to show that then the corresponding two functions on df are the same. So what you do is for each x in df, you just evaluate the equation that you have at the point x and then hope that this gives you what you want. So here we have just kind of evaluated each of the terms at x. And then we see because x is in df, this term is non-zero, so its power is also non-zero. And so here we are allowed to divide this out. This doesn't really play a role here. And this we can rearrange like this, and then we can clear denominators. And so we do check now that even as functions on df, these fractions are the same. So this shows it's well defined, and it's very clear that it's also a K algebra morphism. If you have a sum here, it gets sent to the sum, and so on. And now we want to show this is the bijection, so we just show it's surjective and injective. And surjectivity, and in principle, that's a hard result, but this is exactly the previous proposition. This said that all the functions here can be written as such quotients. Okay, so that was already done. And so we only need to check that it's injective. So assume you have something in the kernel. So assume that you have g divided by f to the m gets sent to the 0 function on df. So in other words, if you evaluate it at any point x in df, you get 0. Well, but then again, f is non-zero, so we are allowed to kill the denominator. And so we just get g of x is 0 for all x in df. Now we want to basically conclude so that g is 0. That would be perfect. But that is a bit too much to ask. But what you can see is that at least after multiplying with one more copy of f, it is true that this is 0 for all x in big X, because we already know g vanishes whenever f is non-zero. And then whenever f is 0, well, this term vanishes. So in the end, for each x, one of these two vanishes. And so you have this equality here. But this just means somehow this is a function and vanishes at all points x in X. So in other words, f times g is 0 in this ring of functions. And that's very good, because this is basically what we need, because now we want to show this here is the 0 element of the localization. So in other words, it's given by 0 divided by 1 in the localization. And by definition, this is just g times 1 minus f to the m times 0. This times some power of f is 0. Again, this kind of slightly tricky definition, but, well, we just take power f to the 1. And then is this equality here true? Well, this is just killed. And so this just becomes f times g, and f times g is 0. So indeed, it is 0. And so this thing was the 0 element. And so the kernel is just a set containing 0. Okay, this shows injectivity. And here, as a summary, we have seen that this ring of functions is just the localization of all polynomial functions on X at the element F.